Hi, I am Prakash Prasad. I am pursuing manufacturing science and engineering from IIT Kharagpur. That is the MTech program. My roll number is 21 ME61R17. And now I am going to present the friction stir welding process and how it can be done using the numerical modeling. That is ANSYS. So let me first take you through the problem statement. Uh, Here 6 mm thickness a plate is given, which is aluminum alloy 6061, and it is to be friction stir welded. And for doing this, a pin is used having a solder dia of 24 mm. The pin height is 5 mm and the pin dia is 6 mm. And the tool rotation speed is 710 rpm. This can be used, and the welding speed is 10 mm per minute. As it is a thermomechanical analysis, so thermal properties such as specific heat and thermal conductivity should also be specified there in the problem setup. And here it is given as the polynomial function of the temperature of degree 4. So generally these four coefficients C0, C1, C2, C3 are fed in the software and it will give the desired result. And the non-Newtonian fluid model is used here. Generally this is the tool interface, and here the control volume is used, and the diameter of 240 mm it is considered, and this rectangular region width is 144 mm, and this is the mesh generation. And the final result or the output what we need is thrust force, welding force, lateral force, welding torque, peak temperature, and weld zone. So now let me take you through the numerical modeling process in ANSYS. I have generally opened the ANSYS. I have already performed the analysis. Just I am showing all the processes and steps what I carried out. First, I went through the fluent. This is here. On double clicking, we'll get this small window open, and from that I clicked on geometry through design modeler, and then I came to this process, this window. So here generally I created the geometry of the plate. This is the plate along with the projection of the pin, which is here. It can be seen here in this. So I will take you through the process. First, in XY plane, I created a sketch. This sketch, as uh, mentioned earlier, the diameter of 240 mm it is considered, and then it is extruded. Similarly, the sketch 2 and sketch 3. Generally, the sketch 1, 2, 3 are generally used for making this plate, and specifically this sketch 3 is used for the named selection of the components and nothing else here. So now let me take you through the name selection. Yeah, these are the named selection. Velocity inlet. This is the velocity inlet, in the sense this is the control volume, and this is the here is the portion where the velocity inlet is given, and it is the portion of pressure outlet, and it is going to the top face here. This is the friction stir welding tool, which is the whole region. This is the cylinder part, and it is the tool region which penetrates inside the workpiece. And the bottom face is here. This is the bottom face, which of less importance. Okay, so after making the model, we have named the selection. These are all the parts, and then it is ready for the meshing. After doing this, I have gone through the meshing portion. Yeah, this is a meshed portion. Generally what I have done is in meshing, initially I did a face meshing here. Face meshing is done with the element size of 0.2 mm. Initially I carried out through zero point 0.5 mm, then zero point 0.4, zero point 0.3, zero point 0.2, and at last I came to a zero point 0.2 mm with a growth rate of 1.15, and it was running good. Initially I used a grain that is growth rate of 1.1, but the number of cells exceeded 5.2 lakhs, which is not acceptable in the student version, so I had to increase the growth rate. And at last, by giving the face sizing of 2 mm here in this portion, that is friction stir welding portion, this is the one thing. And after that I have given the edge sizing here of 0.03 mm, and the growth rate is default. It is done why the small element size is given here, because in this region the tool penetrates here and it rotates, due to which all the temperature variation and the flow of the material is going to occur in this region. So the plastic deformation is going to happen here, and it is our region of analysis. So in order to get the good and better result, it is necessary to provide the element size of, I mean, very small element size. It is necessary, so I have provided it. Only these two things I have provided with mesh, and the remaining thing it is a default mesh. So when I ran the mesh, it produced this surface. I mean, this thing. You can see the mesh here. Here you can see the mesh is very, very small, 0.2 mm, and here it gradually increases with a growth rate of 1.2. And here the region of analysis, I mean, the region of concern is less. That's why here the mesh is coarser, and here is our region of analysis. That's why here the element size is taken as very small. So after meshing, I'm taking you through the setup portion here. In setup portion, when we open directly, we come here. Okay, I'll take you later on here. In setup portion, what I have done is in general I have specified the type of solver, which is pressure based, and the velocity formulation as absolute. And in the model I have turned on the energy equation on, because the flow of energy is going to take place, and as it is a thermomechanical analysis, and the fluid what I have assumed it to be a laminar, that is laminar flow in that weld region with viscous heating. It is necessary to provide these things, and only these two things are provided and everything is kept as off. In material I have specified the A6061 with all the properties. Here the density is constant, with that is 2700 kg per meter cube, and the CP value, that is specific heat value, as I showed you earlier. Specific heat, it is the function of temperature, that is polynomial function of temperature of degree 4. So here the 4 coefficients C0, C1, C2, C3 has to be provided. That value is entered here, that is coefficient, and at last we see how the CP varies with the temperature. This is the variation of the specific heat with the variation in the temperature. It is provided here, and then the thermal conductivity also varies with the temperature, and it is also provided here. Only the coefficients are entered here, and we will get the variation of thermal conductivity with respect to the temperature. And the viscosity, that is a non-Newtonian power law, is considered here, and it is also provided, all the data is provided. The consistency index is taken as 6.88 into 10 power 7, and power law index is 0.0421. Minimum viscosity, yeah, it is going to be around 1200, so minimum viscosity is taken as 1000, and the maximum viscosity as, that is 10 power 6. It is also not necessary, I mean, 10 to the power 4 or 5 can also be provided, then also we are going to get the same result. And the reference temperature is taken as 298 Kelvin, activation energy as 1380, and the primary independent variables, that is static temperature, minimum and the maximum. In Kelvin it is given as 300 and 500. Here these are the properties we have assigned for the thermal properties. And then let me take you through the boundary conditions that I have assigned here in the inlet. Generally, before some time I've showed you which is the inlet portion, outlet portion. Again, let me show you. Yeah, this is going to be the inlet portion, and here the velocity is given. It is to be prescribed, and this is the output portion, output area, output region, where the pressure is to be specified. And this is the top face, and this is the tool region, the small one. This is the tool region. So here I have assigned the velocity in the inlet as 0.00133, which is the absolute velocity in the x direction. And in the output, let's see, yeah, here the gauge pressure is taken, and here the pressure of 1 Pascal is provided in the x direction. Here it is given. And the wall, it is one of the most important setup that we have provided. The wall is considered as moving. It moves with absolute velocity of 0.00133 mm. It is calculated from the velocity which is given here. That is 80 mm per minute. When it is converted to meter per second, then we'll get that 0.00133 meter per second. And this plate, it moves, that is, it translates in the x direction with a velocity of 0.00133 meter per second, and no slip is considered in this case. And similarly, friction stir weld tool, in that it is considered as moving. It will move and it will rotate with an RPM of 74.351 radians per second with a speed of 74.351 radians per second about the z-axis. And even here no slip is considered. And in the top face, you can see it is moving wall, because the whole plate is a single body, right? So everything is moving with the same velocity of 0.00133 meter per second in the x direction. And here also no slip is considered. And the thermal convection is considered as 30 watt per meter square Kelvin. Wait, in this case, yeah, heat transfer coefficient is considered in the bottom phase of around 10,000 watt per meter square Kelvin. It is because here the temperature will be very high, so the heat transfer rate is also going to be very high. So the H value, that is the coefficient, is that is I have taken as 10,000 watt per meter square Kelvin. And after this, named selection methods, report definitions. In report definitions, I'm actually going to find all these variables, that is weld force, lateral force, thrust force, torque, etc. This is a solution. Monitors report, then initialization. Yes, and then finally I'm going to initialize it using the hybrid initialization. Yeah, when it gets initialized, then after that I went through the calculation, radius run calculation. I have taken the number of iterations as 1000. That is, yeah, minimum number of iterations, that is 1000. And after running the calculation, uh, it ran for around 45 minutes, and number of iterations what it took was, here we can see the iteration, that is 478. That is in 478th iteration the solution got converged. Now let me take you through the different plots that is necessary to understand. In graphics, contour, yeah, this plot I have created for, and that is in the weld transverse plane. I have plotted the temperature, and that is to show the temperature distribution. So now let me compute it. This is what we are going to get, the temperature distribution. Yeah, here we can see the temperature, that is the lowest temperature is 300 Kelvin. That is the normal temperature, which ambient temperature which was initialized. And here in the stir region, here the temperature is very high, that is 592 Kelvin, around 592. And you can see the temperature distribution. Here the temperature gets conducted, and heat gets conducted, and the temperature generally, gradually reduces while going away from the this tool region, this weld stir region. Then after that, what I have done, that is the weld temperature distribution on the top face. So generally, I have taken the top face and the friction stir welding tool region. The static temperature is also computed here. Here we can see the temperature how it is going to vary. Here it is a side view, it is not properly visible. So from the top, if you see, the variation of temperature can be seen here properly. Here the temperature is 592 Kelvin, and then gradually it decreases to around here, which is 475, and then here it becomes around 300 Kelvin. This is the temperature, and this is the contour of the viscosity. Generally, wait, let me again tell you. Yeah, contour of the from properties, I have taken the molecular viscosity. Okay, and from here we can see the flow of the material, how it's taking place, and the effect of through the effect of the viscosity. Here we can see that here the viscosity is lower. Here it is lower because this region is very hot, and due to the plastic deformation, as the tool rotates here, it stirs the workpiece, that is the material in this region, and the flow of material becomes easier, due to which the viscosity will also be very low as the material softens here in this region, and it generally increases viscosity. Here you can see it increases from around 1 to 30, around 1000 to 50 kg per meter second, to around here 6 into 10 power 5 kg per meter square. Here the viscosity is very high because it is in the solid region, solid state, and here the weld region, this region can be considered as a non-Newtonian fluid, and thus the viscosity is very low due to the material softening. Yeah. And after that, after the computation, this is the scale residual, where we can see the solution has finally converged after 478 iterations. And these are the few plots what I'm showing, the moment, and here it is not properly visible, but analytical value is shown here. The torque what we are seeing here, it is minus 3.792 into 10 power 1 Newton meter. That is, the torque is 37.92 Newton meter in this case, and the thrust force can is 6.762. The lateral force is 5.91 Newton, and the weld force, it is 18.234. It is the drag force which is in Newton, and generally it is the analysis performed for the element size of 0.2 mm. Initially, I have also performed the analysis in various element sizes. Let me take you through that. Yeah, initially I performed this analysis by considering an element size of 0.5 mm, and then the number of cells what I got is 1,32,000. It is quite low, and the number of iterations it took is 382, and the computation time was very low, that is 8 minutes, and the peak temperature was 591 Kelvin, and the torque what I got was 37.747, and then converted it to get the power, that is 2 pi nt by 60,000, then we'll get in kilowatt. Similarly, I decreased the element size in order to see the variation in the solution what we're getting at the end, and the computational time. Here we can see that when the element size is decreased, then the number of cells increases. Here from 1,32,000 it became 2 lakhs, and the time it exactly, I mean it doubled, around double, like 15 minutes it took. And the temperature, there was no variation, it was same in all the three cases, but you can see that there was a small variation in the torque, very slight variation, slightly increased. And when we consider a cell size of 0.3 mm, and actually this is the growth rate, that is I consider a growth rate of 1.1, 1.1, and here the number of cells was 3,46,000. Here the number of iterations 438. Here you can see that the number of iteration increases as the cell size increases, and also the number of cells also increases, and the time, that is computation time, increases with the multiple, that is computation time multiplies. With 0.3 mm you can see that it took around 8,432, around 4 times as compared to the 0.5 mm, and here it took 45 minutes, a very large amount, like 8 5 40, it's around 5 to 6 times it took 0.2 with 0.2 mm size. But at last when we see all the result, it is almost the same, there is no variation. The peak temperature is 592 in all the case, except in the first case 591. There is not much variation here, it is same, and the torque slightly increases, and there are also not much variation. And here I have plotted the result. This is the results in the graph for the proper understanding. Here the cell size versus the number of cells. As the cell size increases, then the number of cells also increases. And that is from 1,32,000 to 5,91,000. I would have actually uh, taken more smaller cell size with even smaller green growth, but it is not permitted in the students version, so I had to go through the green growth of 1.15 with the element size of 0.2 mm, and below this I was not getting any result, I mean it was not accepting, the number of cells exceeded. And here if you see cell size versus the number of iteration, it gradually increases, not much difference. Here the number of iteration gradually increases, and the number of cells with the simulation time, here you can see the simulation time increases exponentially, that is it multiplies. Initially it was 8, then 15, 30, then 45 with the number of cells, and the peak temperature remained constant, there is no much variation in this case. So from this it can be concluded that I mean I've learned something from here. There was learning moment for me that the appropriate message should be selected because we are getting the same result with different element size with very little variation, as we can see here. In peak temperature there is no variation, and in the torque there is a little bit variation, but that is okay. I mean, it is very close. So here we can go with the element size of 0.5 mm, because if the computational time is very less, it drastically decreases. So in order to get the same result, similar result, it is better to select the control volume size, that is meshing of the control volume with the required number of elements and the element size. And that was the interesting part that I came to the conclusion through this analysis. Thank you.